Hi there, welcome back to our course Advanced Quantum Mechanics. This is lecture 35. We have started to study the Feynman picture of quantum mechanics. Feynman picture. In this case, what we are after is the time evolution operator itself, and in particular, in its representation in the position basis. So we are looking for the Green's function, which tells us what the probability amplitude is for a particle that starts at time t0 at location xe, where the E stands for emitter. So emitting a particle at location xe at time t0. And then we ask what's the probability that this particle shows up at time t at position xd. The Green's function gives us the probability amplitude for that, and it is the matrix element, corresponding matrix element of the time evolution operator. Now, how to calculate that? We could calculate it using the usual operator methods that we developed throughout the course, which is to solve the differential equation for the time evolution operator. But Feynman, and that's the significance of the Feynman picture, Feynman found another way to calculate the Green's function. In fact, a way that doesn't involve any of the techniques that we've developed so far in this course. Feynman arrived, after lengthy calculations, at an alternative formulation of quantum mechanics. In particular, Feynman showed, and this is how far we got last time, that the Green's function can be expressed as the path integral over the probability amplitudes for the particle to take a path from the initial position where it was emitted at the initial time t0 to some location x1 at time t1, and then onwards to various other locations, eventually to location xn at time tn, and then onwards to our detector at position xd at time t. And we need to integrate over d3x1 to d3xn. So we have we can insert here any large number of intermediary times and locations if we so wish. And then we let n go to infinity. So we subdivide the time interval from t0 to t into infinitely many tinier and tinier portions. So we let n go to infinity to obtain that the time interval t minus t0 gets subdivided into n portions, which we call delta t, and that goes to 0. And then we write the proper path integral, which is what we get in that limit. Namely, we then have that the Green's function xd x e t t0 is equal to the path integral over all paths of the probability amplitude for some for one of those paths here, right? So we pick any one of all possible paths, and for this path, we then take the probability amplitude path from xe at t naught in some way to the detector at time t. And then we symbolically write here dx of t. We are summing over all possible paths. For each path, we calculate the probability amplitude, and then we have to sum it up for all probabilities, for all paths. So this is the Feynman path integral. Now, this looks like it's a lot of work. Namely, we have to insert all those intermediary points in time, and then if you remember how we arrived at this, we had to insert resolutions of the identity, and yeah, we get infinitely many of those as capital N goes to infinity. So to calculate it in the way that we did here is tedious, and it involves that we know the Green's function for the intermediate pieces of the path. It involves knowing the time evolution operator. So the way that we express the Green's function here in the path integral way is not actually saving us any time or work. It doesn't seem useful at this point. But, and that's crucial, Feynman figured out that we can work out what this path integral is without having to solve for the individual time evolution operators from time t5 to time t6, and then time evolution operator from time t6 to time t7, and so on. No, there is a much more elegant way of expressing what this Green's function is as the path integral. Namely, by finding an elegant way to calculate what the probability amplitude is for a given path. We don't have to subdivide the path the way we did so far. In fact, there's a much more efficient way to do that. And this is what we are going to do now. So, how to calculate the probability amplitude for a path efficiently and without needing any quantum mechanical tools. This is possible. And because we can calculate the probability amplitude for a path without knowledge of anything that we did so far in this course, because of that fact, the Feynman path integral can stand on its own. It is an alternative way of describing quantum mechanics from scratch. So how do we do this? How do we calculate the probability amplitude for a path? We use what we know, what we learned throughout this course in order to calculate what the probability amplitude is for a path. But once we have the relevant formula, then we can calculate the probability amplitudes for all paths without needing anything quantum mechanical. It turns out that the answer is very simple in the sense that the answer has an expression in terms of something entirely classical. So how can this be? How can it be that how can Feynman's approach avoid using the quantum mechanical tools that we developed? here's the gist of it. Let me first explain why quantum mechanics is hard. So, why is quantum mechanics hard? Now you may guess why that is. It's because the x and the p are not commutative, right? So that's the question. Answer: x hat, p hat, commutator not equal 0. That's why we need all this business with the Hilbert space representations, and it just gets complicated. Now, let us have a look at what would happen if they were commutative, but other than that, things would be like in ordinary quantum mechanics. Let us dream for a moment what would be if they were commutative. Well, let's see. When we want to calculate the Green's function, like xd, xe, t, t naught, then this is xd, and then we have the time evolution operator. Let's choose a particular Hamiltonian so that we can make things concrete. So let's say the Hamiltonian is the Hamiltonian of a free particle that we expose to a potential. This could be Coulomb potential, harmonic oscillator potential, non-harmonic oscillator potential, whatever. That's typically how a Schrödinger electron problem looks like. So in this case, our time evolution operator that goes in here for the calculation of the Green's function is e to the power of t minus t naught divided by IH bar, and then the Hamiltonian. And the Hamiltonian is p hat squared over 2m plus v of x hat. And then here we have the emission position. Now, if the x hat and the p hat were commutative, so if the x hat, p hat, well, let's not put it this way. Let's just say if, let's say, assume we would have, because it's not actually true. But you see, Feynman has a way of making it true in a very sneaky way. So assume we would have the following. Assume we would have that this is equal to xd, and then we could take these two terms here, the kinetic term and the potential term, separately. Assume we could do this. How would it look like? Well, then we would have here t minus t naught over IH bar, p hat squared over 2m, and then e to the power of t minus t naught over IH bar, v of x hat, and then xe. Keep in mind never to write this in an exam, because it's not true, right? This is not actually, I should put this here, right? This is not actually true. But at the moment, let's just consider what would be the case if it were true, for example, in a really good approximation. So if this were true, then that would be fantastic. I mean, first of all, why is it not true? Why is it not true? Because the x hat and the p hat are not commutative. Therefore, you know, if you can't just take this apart, if we multiply that one with this one, why would that? It's just not true, right? Okay. But if it were the case, then we could immediately write down that this is xd, and then e to the power t minus t naught over IH bar, p hat squared over 2m. So far, everything as usual. But then we could put the xe here, and this part becomes number valued. Why? Well, because the position operator is acting on a position eigenvector, So therefore, we would simply have e to the power of t minus t naught IH bar and then v of xe. That's nice, right? Because this has lost its operator character. Now, that here is still a momentum operator, and we need position matrix elements, but we can handle this. We know how to do this. We insert a resolution of the identity over here. So we can write this as xd e t minus t naught over IH bar p hat squared over 2m, and then a resolution of the identity p xe, and then e to the power t minus t naught IH bar v of xe, and then dp, right? I just inserted a resolution of the identity, and nicely, this means this becomes number valued now. So we would have then that this is the integral of what? Well, xd, and then p, and then this just pulls out as a number. It's e to the power t minus t naught over IH bar, and then p squared over 2m. And then, that p is over here now, and then we have here a p xe, and then we have e to the power t minus t naught over IH bar v of x naught dp. And these matrix elements are always the same. We know what they are. Integral 1 over 2 pi h bar to the power of 3/2. We're working here in 3 dimensions. Why not? So that's why there's a 3 here. And then e to the power of IXD p divided by h bar. Right? That's what this is here is. And then we have e to the power t minus t naught over IH bar p squared over 2m. And then this is again a factor of this kind here. We have e to the power of minus I xe p divided by IH bar. And then here we have 2 pi h bar. Up. 2 pi h bar to the power 3/2 from here. And then we have e to the power t minus t naught IH bar v of x, what is this one, e, and dp. This is an e. All right. And in principle, we are done now, because all we need to do now is that we need to integrate over p, and then we have our Green's function, right? And we can integrate over p. Why is that? Well, it's because here we have something that's linear in p, something that's linear in p, here is quadratic in p, and that thing doesn't depend on p. Oh, I made a mistake here. This goes up into the exponent, of course. This is up here, v of xe. Sorry about the software here, it messed this up. Sometimes does this. All right. So all we need to do is what is called a completion of the squares. Because we have here a polynomial of degree 2, we can always write this as p minus something squared. And then it becomes a Gaussian integral, and the Gaussian integral can be performed. And so we can carry out the momentum integration, and we can work out explicitly what, therefore, the Green's function is. This would be true in fantasy land, where e to the power of the sum of 2 operators is e to the power of 1 operator times e to the power of the other operator, even though they're non-commutative. That's not true, but here's the thing. This is for a finite amount of time evolution. It could be a long time evolution, right? It could be a long time between we release an electron and ask, does it arrive over there? It could be 5 minutes later. Or it could be our neon atom of the previous lecture. You know, we release it someplace and then we check 5 minutes later whether it's some other place. Then in that case, that is definitely not this. But, and this was a crucial observation of Dirac that Feynman picked up on. Dirac realized that if that time interval is tiny, for example, these tiny time intervals that arise when you subdivide the total time interval into n smaller ones in order to get the path integral. So whenever you have a super tiny time interval up here, then actually this becomes approximately that. Because, see, then this becomes approximately that. And the approximation becomes the better, the smaller the time interval becomes. See, that's the magic that Feynman utilized. The fact that this normally intractable thing where you simply cannot go that route that we outlined here. See, if you could do that first step, then the rest would be easy. And in particular, you could calculate the Green's function without knowing anything about quantum mechanics. You just have to integrate over P, right? It's just reduced to an integral. And Feynman does that. What Feynman did is, he said, let's subdivide the time evolution operator into a product of lots of time evolution operators. And then for each one of them, there's just a tiny amount of time evolution, small delta t, then this is true. And then we can do this bit. And then we have to do one of these momentum integrals for each one of these little time intervals. But this can be carried out, this momentum integration. And so we get a definite answer for the Green's function for one of those tiny little time steps. And the product of all those, we can then work out. And this is how Feynman arrived at his beautiful formula for what the probability amplitude is for a path. So what we need is the mathematics of going from here to there for small delta t. This is called the Trotter product formula. We now use the Trotter product formula. How does this work? Or I should say introduce. We now introduce, because we are going to use it soon enough, but this is the introduction of it. Introduce the Trotter product formula. All right, so assume A hat, B hat are self-adjoint and may not commute. This is our situation, namely here. You see the p squared over 2m is an operator like A. Actually, the whole thing here would be the operator A. And then this multiplied with that would be our operator B. So let's assume that we have two self-adjoint operators and they do not commute. Then we have clearly that e to the power I A hat plus B hat is not equal to e to the power I A hat, e to the power I B hat. If it were true, well, then we would be in business, right? Because then that would be the step from here to there, and the rest is easy, and we end up calculating the Green's function pretty easily by just doing completion of the squares and integrating something. All right, so that's not the case, but the Trotter product formula helps us do something about it. So define C hat to be the operator A hat plus B hat. Now, C hat definitely commutes with itself. So what we can certainly say is that e to the power of I, A hat plus B hat, which is C, is equal to e to the power of I half A hat plus B hat times e to the power I half A hat plus B hat. You see, there's no problem with non-commutativity here because this is C, this is C, this is C. C commutes with itself, therefore everything works just as if it were numbers. Okay, so we have this, and therefore we also have e to the power I A hat plus B hat is equal to, and now it's getting interesting, it is equal to e to the power of I divided by n A hat plus B hat to the power of n. Right? So instead of dividing by 2, I'm dividing by n. So by the same logic as here, still true. And that's because the A hat plus B hat is just like one operator and it commutes with itself. So therefore the usual rules of exponentiation apply. So we still have that this is true. But you see, now we can make this number very small because we can make capital N as large as we want. So this gets very small. That's what we are aiming at. You see, when we subdivide, for the purposes of deriving the path integral, when we subdivide the time interval into n portions, and we get expressions like this. All right, so let's look at this. Let's expand. We observe that e to the power of I over n, a plus b, is what? Well, by definition of what the exponential is, this is the identity operator plus linear term I divided by n, and then a hat plus b hat plus stuff of the order 1 over n squared. Right? And we also have that e to the power I over n of a hat is identity plus I over n, and then the linear term a hat plus, let me just spell it out, it would be I squared over n, n squared over n squared with a factor of 2, and then a hat squared plus dot dot dot. But all of this we will simply write as order of 1 over n squared plus order of 1 over n squared. So this stuff decays faster than that. And similarly, we have e to the power I over n, b hat equal to 1 plus I over n, b hat plus terms of order 1 over n squared and higher. See, let's look at this very carefully. What happens now if we write down the product? If we write down e to the power I divided by n a, e to the power of I divided by n b. You see, we wished that this would be that. It's not, but maybe it's approximately. You see, calculate what this product is now. So this then is 1 plus I over n a hat plus order of 1 over n squared times 1 plus I over n b hat plus stuff of order 1 over n squared. And what is that? Well, there's the 1 times the 1, so that's 1 plus I over n. It's this term times the 1, so it's a hat And then we have the 1 times this term, so it's plus b hat plus, well, all other terms are of order 1 over n squared or higher. You notice that this is the same as that. So what this means is that even though this term is not the same as the product of these two terms, when n is very, very large, it's approximately that, right? Because for n very large, we only have the identity plus the first leading term, and they are the same here. So we have, so therefore we have that e to the power of I over n, and then a hat plus b hat is equal to e to the power I over n, a hat e I over n, v hat plus order 1 over n squared for large n. Now, remember that we had this. We had that e to the power I, a hat plus b hat. And in our case, this is going to be the full time evolution. This is the time evolution of a little step, because we divide by n, right? But that's the full time evolution. So the full time evolution is this thing to the power n, right? So we have, recall, e to the power of I, a hat plus b hat is equal to e to the power of I over n, a hat plus b hat to the power of n. That's an n here. All right. But we also know that this is approximately that. It becomes that when n is very large. So that then becomes approximately, for very large n, this becomes e to the power of I over n a hat, e to the power I over n b hat to the power of n for large n. And what we see here is we conclude, and this is the Trotter product formula. We conclude that following is true. E to the power of I, a hat plus b hat is equal to the limit n to infinity, when all of this becomes exact here, limit n going to infinity of e to the power I over n a hat, e to the power of I over n b hat to the power of n. And you see, each one of these factors here is like our best case scenario above, right? But we have basically, this would be the p squared over 2m term, and that would be the potential term. And we know how to handle those by, using a resolution of the identity and so on. So let's apply this now. Our time evolution operator, the one that we are really interested in, that goes to time t, starting from time t naught, is e to the power of t minus t naught over IH bar, and then p hat squared over 2m plus v of x hat. So if we now identify what our a hat and b hat are, we have that a hat here is t minus t naught divided by IH bar. I'm sorry, the I already contained here. So it's a minus. And then p hat squared over 2m. That's our A operator. And then the B hat operator is minus t naught divided by H bar V of X hat. And then we have that u hat of t and t naught is not equal to e to the power of t minus t naught over IH bar p hat squared over 2m times e to the power of t minus t naught over IH bar v of x hat, which is what you could easily handle if it were true. But we have something that's almost as good. Namely, we have that u hat of t and t naught is equal to, by Trotter, it's the limit for n going to infinity of e to the power of 1 over IH bar and then t minus t naught over n, which is something that we will now call delta t, times p hat squared over 2m multiplied with, and so this is a nice factorization here, 1 over IH bar and then t minus t naught divided by n, so that's the delta t again, v of x hat, and to the nth power. All right, so now what we will do is pursue the exact steps that I outlined in Fantasy World earlier. Remember? We said that here, if the Green's function was, the Green's function is of course always this expression, but if that factorized, if it did factorize, then what would we do? What we would do is we would first of all have here this thing that only contains the position operator. So therefore the position operator in here just becomes eigenvalue times the identity. So we can pull this out. And then we are left with having just this expression here. And in order to turn this number valued, we just insert a resolution of the identity in terms of the momentum eigenvectors. Then this becomes a number which we can pull out. Here it is. And then we're left with number valued, and then these overlap functions, right? The xdp and the pxe. We know what they are. It's just the position eigenvector and the momentum basis, and the momentum eigenvector and the position basis. They're just given by these Fourier factors, e to the power ixp, or e to the power minus ixp, divided by that normalization here, right? This step, all of this we can now do. We can do it for each one of those tiny time intervals here. So let's see. Here we are. Here's the time evolution operator, the full time evolution operator that we now write as an infinite or finite product of operators, but we let the number go to infinity eventually. So what do we have? So we have g of xd, xe, t, and t naught. is equal to, well, xd and then u hat of t and t naught and xe. And this is now equal to the limit n going to infinity of. And then we have here the xd. And then we have all that business over here in here. So we have, let's try to spell this out, 1 over IH bar. And then we write here delta t, and then p hat squared over 2m, and then e to the power of 1 over IH bar, t minus t naught divided by n, and then v of x hat. And this factor we have n times, right? So we have here, let me see if that works. Maybe that works. Perhaps just copy this. Yeah, it does. Almost. Copy and paste. All right. So, and right, and here we would have xe. Yeah, so that's the n powers here of this factor. Oh, just a sec. This is a delta t here, and same here. That's a delta t. Delta t. Okay. Now, an immediate benefit that we can reap here is that, as we saw before, this exponential of something with a position operator immediately becomes a number valued thing that we can pull out here, and it just becomes v of x e. So that's an easy thing to do. But then we're not yet done, because we still have all these momentum operators, and then we also have these position operators. So what we can do here is we can insert resolutions of the identity in here. So here we insert the resolution of the identity in terms of momentum vectors. This is all in 3 dimensions. So let's call it n, and then d3p, minus infinity to infinity. And here too, here we would insert then a resolution of the identity. Whenever there's a momentum operator, we insert the resolution of the identity in terms of momentum. Integral Pn minus 1, Pn minus 1. And whenever we have an in between here, I mean, in this case, we don't need it, but for example, actually, this one has to move. Okay, so let me just write it like this. We write down a resolution of the identity in the x's as well. xn, d3x, and this also goes in here. Or let me write here xi. xj. Okay. So what you see here is this is an operator that contains the momentum operator. Here's an operator that contains the position operator. Then again, there's one with the momentum operator. Then again, there's one with the position operator. They keep alternating here from left to right. We don't want any operators left over, so we insert resolutions of the identity in the position representation and in the momentum representation, n of them, n resolutions of the identity in position representation, n resolutions of the identity in momentum representation, spread over this entire business here with so many operators. And what do we obtain when we do this? Well, we obtain plenty of integrals, right? we obtain the limit for n going to infinity. And then we have integrals, plenty of integrals. Namely, we have 2n integrals. We have actually 6n integrals because we have n times 3 position integrals and n times 3 momentum integrals because everything isn't happening in 3 dimensions here, let's say. And all of those operator valued things become number valued things. So what we obtain here is contributions from these. We obtain here terms of the form e to the power of 1 over IH bar delta t, and then p squared over 2m. In the first case, it would be a pn squared over 2m. And then we also get a term where we have e to the power of 1 over IH bar, and then we have delta t, and then a v of xn. And it keeps going like this until we have, a term of the form 1 over IH bar delta t, and then we have a p1 squared over 2m, and e to the power of 1 over IH bar delta t, v of x1, or the xe actually. But we're not yet done, because not only do these operators become number valued, because we have these resolutions of the identity which make them go into those various eigenvalues. No, we are also left with the inner products of the x and the p's. Let me show you. We've seen this before. Remember in our fantasy world calculation here, where we said, if only this was true, well, now it's approximately true, right? In the limit, it is true for the small intervals. Then what did we do? We said, okay, the v of x hat immediately becomes this factor. We do this too now, but we have to insert a resolution of the identity in the position representation, because not all of these v of x hat operators are at the rightmost place. So if it's somewhere in the middle, then we have to insert a resolution of the identity in the position representation. But then we are left with this expression where we have position matrix element of a momentum operator involving function. So we put the resolution of the identity in momentum in here, okay? And then this becomes number valued. That was number valued already, but then we are left with these factors as well, okay? And these factors are just Fourier factors, 2 Fourier factors, right? And that's what we get down here as well. So not only do these operator functions here turn into number valued functions after inserting so many resolutions of the identity, but we also get times, and then we have 1 over 2 pi h bar to the power of 3/2 squared, because we have 2 resolutions of the identity, 1 for the position, 1 for the momentum. And then we also have to take it to the power of n, because we do this n times, right? So we get this factor here. We get this to the power of 3n. And then we get these overlaps, these Fourier factors, and they are of the form e to the power of I, and then it's something like pj times xj minus xj minus 1. Now, I don't want to go into all the details here because you have to be careful with the very leftmost term, because it has the xd, and the very rightmost term because it is an xe. And exactly how those Fourier factors combine there. But in the lecture notes, with a lot of work, I wrote down the full shebang, the whole story of how all of this works in all the details. I wrote it up for you in the lecture notes. But it would take us too long to go through all of those details now in the recording. I think you'd be bored to death. It's much better you could read it in the lecture notes at the speed and at the detail that you prefer. All right, we're almost done with this formula. We should not forget that we have d3x1 all the way to d3xn and d3p1 to d3pn, because we inserted so many resolutions of the identity. Now, similar to what we had in the Fantasyland calculation, similar to that, we now have in the real world that when we look at what we are encountering here in the exponent, then we have, as far as the momentum is concerned, we have only p² terms and terms that are linear in p, like this one. No, that one is quadratic in p. And we have linear terms, namely those from the Fourier factors. As far as the x are concerned, we can't say anything in generality, because the v of x could be anything. It could be like a 1 over x for a Coulomb potential. It could be an x² for harmonic oscillator. It could be an x to the 8th power for a non-harmonic oscillator, for example. So we can't make general statements here for arbitrary potentials, but we can say what's going on with the momentum, namely at most quadratic terms. And when we have at most quadratic terms, then we have a chance to complete the squares and to do an integration, a Gaussian integral. So let me sketch how that works. We can integrate the pi using completion of the squares. Our integrals look like this: integral minus infinity to infinity, and then we have e to the power of I times p, and then we have a linear term. Just a sec, let me write this nicely. So there's a linear term ap and a quadratic term p². Right? That's how all of these integrals look like. I mean, there's a p1, there's a p2, there's a p3, etc. But we have them linearly and we have them quadratically. So each one of these pi integrals here, we want to perform these now, is of this form. And how do we evaluate an integral like this? Well, we complete the squares. We write this as an integral from minus infinity to infinity, and then it's e to the power of I times b, and then check what I'm doing here, plus a plus 2b squared. If we write this, we get definitely the IBP² term. We also get the linear term IAP, because we get IB P, and then divided by twice, because it's a mixed term, divided by 2, the 2 goes away, the b goes away from here, and then we have the linear term a, so we get that too. But we have one extra term that we now have to get rid of. That's minus I, this thing squared, and so that's going to be a² over 4b. It would be 4b², but there is a b here that cancels that. All right, so it's this, dp. It's just a reformulation, right? We didn't really perform an integral yet. And now we see that this doesn't depend on p. So we can pull this in front, and we have e to the power minus I, a² divided by 4b, and then the integral from minus infinity to infinity, eib. And then that integral we may call integral over p tilde squared, dp tilde, for p tilde equal to p plus a over 2b, right? Because the integration measure doesn't change, and so we can just write that. Also, the boundary doesn't change, so we can write it like this. And this here is what? Let's give this thing a name. It's called, let's say, mu. Then this is e to the power of minus I a squared divided by 4b times mu. Mu is some sort of constant, right? Now, what is mu? If, strictly speaking, mu is divergent, because this is a phase, its modulus is 1, and we integrate that from minus infinity to infinity. If we were lucky, we would have non-absolute convergence, but we are not. This thing is actually divergent. Mu is infinite. But if we choose temporarily to give B a tiny positive imaginary part, then we get a term e to the power minus p tilde squared. And that makes it very convergent, because then it's Gaussian. The phases don't disturb that the Gaussian decays so fast, right? So even the tiniest of imaginary parts in B makes this thing convergent. Now, we will not worry about this. In practice, if you want to really work out what the path integral is, even with a normalizing prefactor, because that's all it is. This is just a normalization constant here, the mu. It's just some constant. If you really want to work that out, then you can do this. You can give the B a tiny imaginary component. This corresponds to the mass of the electron being temporarily given a tiny little imaginary part. Then you can make that finite. Anyway, we will not worry. We will just keep this as a prefactor for now. And then we have calculated our integral, right? So whenever we have an integral that is a phase function with a linear and a quadratic term, as we have n times in this path integral, in this integrand, then this is how we can integrate it. So let's identify now what the A and B are. Here we have that A, see, A and B, these two constants we can read off from looking at, the B is the prefactor here, it's delta T over IH bar to M, and the A here is IH bar, it's delta T over IH bar, right? The I has to be pulled out because the I is pulled out here as well. So what we obtain is that A is equal to xi minus 1 divided by h bar. I mean, for each one of these P integrations, we get an A, right? And then the B is equal to minus delta T divided by 2mh bar. And so therefore, the all-important term A squared over 4B is equal to A squared over 4B is then equal to minus xi minus xi minus 1 squared. And then here we have a 2mh bar divided by 4h bar squared delta t. Of course, the 2 cancels with the 4 to give a 1/2. This h bar cancels this. Okay, so it's a minus xi minus xi minus 1. Oh, how did this happen? And that's squared. And then we have here an m. We have an m. And we have a 1/2, 2 divided by 4. And we have here a h bar and a delta t. All right. So therefore, we can now work out what this path integral here is, and therefore what the Green's function is. And as I said in the lecture notes, I give you all the details. We don't need them, all the nitty-gritty details for now. So G of xd, xe, or xd, xe, t, t naught is then equal to the limit n going to infinity of integral, many of them, and then 1 over 2 pi h bar. This is from those Fourier factors to the power of 3n. And then e to the power of delta t divided by I h bar, and then all those potential terms. And the potential terms can be written like this: I equal 1 to n, and then it's simply v of xi. And now from the momentum integrations, when we carry them out, then we obtain that this is mu n, this universal prefactor there, times e to the power of minus 1 over I h bar. Sorry about this. I don't know how it does this. 1 over I h bar. And then 1 over 2m. See, what I'm using here is a squared over 4b, right? Because our integrals, our momentum integrals, evaluate to this. And the a squared over 4b is that. So we get, and now magically something very nice is emerging here, namely 1 over 2m, and then we have the sum of one term for each of the momentum integrals here to n, of xi minus 1 squared. And then we can write this here as divided by delta t squared times delta t. There was only a 1 over delta t in the denominator, but I can write 2 of them if I put another delta t in the numerator. And that's because here we also have a delta t and the sum. Well, and then we still have the position integrations left over, d3x1 all the way to d3xn. You see, the beauty of this is now that as n goes to infinity, and therefore delta t goes to 0, we get more and more terms here, and these two become Riemann integrals. Same here. This one as well. This and that. They become Riemann integrals. And therefore, the Green's function here can be written, and we are now arriving at the grand finale of Feynman's calculation here. This is a normalization. It is the mu to the power n divided by 2 pi h bar to the third. Well, let me just write it out. Let's just write it's mu. It's a normalization constant. And then the integral over all paths. Right? Because just like when we first encountered the path integral, we still have a subdivision of the time interval into small portions of length delta t. And we still integrate over all positions at each of these time steps. So we still have the path integral here. So what we obtain here is that this is then e to the power of I over h bar. That's from here. See, this is I over h bar. And here then this is minus I over h bar. And here we have something that we call the action. And it is simply the collection of these terms up here. I'll write it down in a moment. And then here, symbolically, this thing is written as dx of t in the actual limit for n going to infinity. Where? What is this action? Well, the action of x of t is equal to, well, this becomes a Riemann integral here, right? And that Riemann integral is the integral from t naught to t of, well, let's look at what we get. 1/2, and then, oh, this m is, sorry, it's not in the denominator, it's in the numerator. We get 1/2 m, and then, what is this? This is delta x over delta t. That's the velocity. In fact, it's the velocity squared. You see, the reason why we put a delta t squared in the denominator is so that we get the velocity squared here and a delta t that makes the whole thing into a Riemann integral. So what we have here is x dot of t squared dt. That's a bit too early for the dt. Minus this piece. Why a minus? Well, because here's the I is in the denominator, there it is in the numerator. That's why this minus becomes a plus and this plus becomes a minus. So we have here then the integral of the potential. So here we have v of x of t, and then dt. And this expression here you may recognize as the so-called Lagrangian of x. Oh, how did that happen? X of t. This is the Lagrangian. And did I give it a name already? This is called the action. This is the action of the path. For every path, we can now assign a number, which is the action. Now let's compare with what we had before. We had that g of x d x e t t naught is the integral over all paths of the probability amplitudes of the path d of x of t. And now we know that this is equal to g of x d x e t t naught, right? Let me just show you that this is really where we started from. See, this is that by the Trotter formula, and then inserting resolutions of the identity, and then completing squares and integrating out the momenta. This is what we obtained here. Path integral is this expression. And we also know that it is this expression. So therefore, from this, we conclude, therefore, the probability amplitude for a given path, x of t, is equal to e to the power of I over h bar, the action of the path, x of t. Right? So this means that our neon atom, for example, if it travels through vacuum from one point to another, has a finite probability amplitude to take any arbitrary path. And the probability amplitude that it takes a particular path is obtained by taking the path, x of t, plugging it into this formula here, which doesn't involve any quantum mechanics. In fact, it is the classical action. plugging into this formula, getting a number, the so-called action, and then e to the power of I over h bar times that number is the probability amplitude for the particle to have taken that particular path. So what we have now is a completely new way of calculating what the Green's function is. The Green's function for x up d x e t t naught is, all paths, and then e to the power of I over h bar s of a path x of t, and then we have to sum over all possible paths x of t. And you see, all you need to do to obtain this Green's function is, in principle, write down the first path that comes to mind from the given starting position to the given desired ending position, calculate using the action formula, here, this one, calculate what the action is for that path, plug it in here, get the probability amplitude, and then do this for the next path, and add its probability amplitude, and so on. And eventually, if you do this for all paths, then you get the Green's function. There's a normalization factor here, but let's not worry about that one. After all, we can always fix that by using the fact that we know that the Green's function at t equal t naught is the identity. Right? The Green's function is just the Dirac delta at t equal t naught, and that allows us to fix the prefactor there. All right, so this is Feynman's way, in principle, to calculate the Green's function. And remember that once we have the Green's function, we have the time evolution operator, we have everything. And as I promised, Feynman's method doesn't involve doing any of the usual quantum mechanics, using any of the tools that we would normally use, the tools that we developed in the first part of this course. I mean, so far in the course, we need nothing of that. Instead, all we need is choosing paths, plugging the path into the action formula, calculating the action, and then integrating that up. But the integrating it up is, of course, the difficult part. How do you do this? How do you integrate over paths? In principle, you can do it the hard way, and you do it by discretizing the time axis and then inserting and then integrating over all possible locations where the particle could be, and in this way you parameterize all possible paths, and that's basically not possible for quantum mechanics. It's just too hard to even make well-defined. It turns out that when it's a random walk that is of observed particles, so-called Brownian motion, then it can actually be done. But with these probability amplitudes, rather than the probabilities, it cannot be done, because these guys don't converge fast enough to have good control over it. Whereas if this is Brownian motion, then the paths cannot be too wild. But in quantum mechanics, there's nothing that constrains the wildness, the jumpiness, the discontinuity of the paths. So that's super hard. But as I mentioned in the previous lecture, this is not how we usually perform path integrals. Instead, we perform path integrals by starting with a path integral that we can carry out. For example, if the S here is simply quadratic if the S is quadratic in X, in the path, then this path integral is of a Gaussian form, and it can actually be carried out completely. Yes, with some regulators and so on, but it can be done. And so you know the Green's function then. But then you may, in practice, have to work with an action that's not quadratic. What do you do then? Well, then you can do a Taylor expansion of the terms that are not quadratic. And then you can do integration by parts or substitution in the path integral formally. And this is how you can then also perform path integrals for non-Gaussian integrants. This is all very difficult and risky because it often is not true that you can interchange a Taylor expansion series, which is a limit taking, with the path integral. But we do nevertheless, and we do it very carefully. But I want to point out here is that the difficulties of the path integral, the analytic difficulties of the path integral are ameliorated in the same way that the difficulties of the Riemann integral are ameliorated. The Riemann integral is difficult to carry out. If you want to calculate the Riemann integral over a cosine, for example, it's really messy because you have to, subdivide the axis in infinitely many little partitionings and then sum up the areas of the rectangles. Nobody integrates the cosine this way. Instead, we use tricks, right? We Taylor expand, for example, the cosine, and then we integrate every term in the Taylor polynomial, in the Taylor series, right? And then we find out that it's the sine, the antiderivative of the cosine. So similar to this, where in ordinary integrals, we usually don't integrate by going back to the Riemann integral definition. We integrate by using integration by parts and substitution. Similarly, we handle the path integral in quantum series, especially in quantum field theory. Now, finally, I want to make some comments about how the path integral picture of quantum mechanics relates to classical mechanics. Remember that when we first started in this course, we said that Newtonian mechanics cannot easily inspire us to come up with quantum mechanics. Instead, we followed Dirac and we said classical mechanics can be written on a more abstract level. Instead of just writing down Newton's differential equations, of which there can be many if the system is big, we write down instead the Hamiltonian, the total energy. And then with the Poisson brackets and so on, we can calculate all the equations of motion. So the Hamiltonian is more abstract because from the Hamiltonian, we can derive the equations of motion. And then you remember from the Hamiltonian picture of classical mechanics, we went to quantum mechanics by checking whether we can have some non-commutativity. And then we found yes, a special kind of non-commutativity, yes. And then we looked at the representation theory and the whole quantum mechanics followed from that. That's not how Feynman's picture looks like, right? There's no non-commutativity left in this. In Feynman's picture, look at what we have. We have to come up with classical paths, just number-valued paths, position-valued paths, and then just take all of them, give all of them a probability amplitude, and then sum them up. There is nothing non-commutative anymore. Because in this Trotter limit, remember that the non-commutativity didn't seem to play a role anymore. So what then does Feynman's picture tell us about the relationship between quantum theory and classical theory? Well, it turns out that instead of doing this, from going from the Hamiltonian to the equations of motion of Newton, the differential equations of Newton, and then going to the functions x of t, p of t, etc., to numbers, number predictions. And there we then were inspired to get to quantum mechanics with the Hamiltonian, and then we had the equations of motion, we had the canonical commutation relations and the hermiticity conditions, and from there we then went to the f hat, and then from there introducing the psi, we ended up with the f bar, and they are number value predictions, right? So that's one way to do this, and that's what we did throughout this course. But there is another way, namely, this is the Feynman way. We can go from, we can instead do this. We can say that, how to write this? classical mechanics, here's classical mechanics, and here's quantum mechanics, and classical mechanics can also be written here with the Lagrangian on top. And then we get the differential equations of motion of Newton and etc., etc. Classical mechanics here has the Lagrangian and the action. And what we see here is that, again, this can inspire us to obtain quantum mechanics. Namely, what we now obtain is that the path integral here is EIS of x, d of all x, right? I mean, x of t. And from there, of course, we get the Green's function, g of x, dx e t t naught. And from there, we get the time evolution operator u hat of t and t naught. And from there, we get, you know, the f hat, we get the f bar, etc. So we know that this is equivalent quantum mechanics to this one. But what exactly is that relationship here? Now, remember that in classical mechanics, I hope you've seen this before, in classical mechanics, we have the action principle. So here, this here, so classical mechanics in Lagrangian form. How does it look like there? Well, there we say consider all possible paths x of t that our particle could take, and then calculate the action for it, very similar to what we do in the path integral, right? So we take a possible path and then calculate the action for it. And then the action principle says that the variation of s with respect to the path x of t ought to be 0, which is to say that the action should not vary to first order as we vary the path. If, for example, this is a path from xe at t naught to xd at t, for which this variation is 0, then if we do a little bit of a detour here, that would also be a path, but it wouldn't be extremal. So the point is that if we do a little change of the trajectory, then s would to first order not even change. Now, this can be shown to be equivalent to the Euler-Lagrange equations, which are dl by dx of t minus d by dt of dl by dx dot of t equal to 0. Now, often people say that this is the so-called least action principle. But now we see that's a misnomer. We should not call it the least action principle. And the reason is that coming from quantum mechanics, we can now understand more deeply why this makes sense for classical mechanics. And the reason is this. When you look at this path integral here, you see that it has a very oscillatory integrand. And one can show that most of the contributions to the integral cancel themselves away because of the oscillations, because they're as much positive as they are negative, and the same in the complex plane. The chief contribution, the main contribution to the path integral, comes from that path which has that the action doesn't change to first order. And the reason is that it is reinforced by its neighbors. Because this path, the one for which ds by dx is 0, is not only itself contributing to the path integral, no, its neighbors, those which are just very close, very similar paths, they contribute very similar action, in particular with the same sign. So they reinforce each other, they add up in the path integral. So the dominant contribution comes from that bunch of paths which have the most similar action. And those are the paths around that path which has the extremal action. And now we see that the least action principle should really be called critical action principle. And that's because what matters for having the most contribution in the quantum mechanics here is not that the action is minimal or that the action is maximal. No, it's just that it's critical. The only thing that we need is that the phase factor here, the probability amplitude, is stationary. It doesn't have to be maximum or minimum. It has to be stationary with respect to perturbations of the path. And indeed, there are cases where it's not the least action principle, but the maximum action principle. Take, for example, the motion of a point particle relativistically in curved space-time. Its action is the proper time along its path. And the path that it takes, according to classical general relativity, is the path of maximum proper time, not minimum proper time. So what we see here is that quantum mechanics, in the form of Feynman's path integral, explains why quantum mechanics can be expressed as the theory of paths with critical actions. And we now also understand from Feynman's perspective what quantum fluctuations are. Quantum fluctuations are contributions to the path integral which are not directly at the extremal action. As much as they contribute, quantum mechanics deviates from classical mechanics. All right, so this is our treatment of the Feynman path integral so far. And I will see you for the last lecture on Monday. Okay, bye-bye then.